Good morning, peeps. How we doing? Okay, let us commence. I assume people can hear me?
Yeah.
Okay, coolio. So I passed out. I posted the final exam on last night, on yesterday. Yeah, yesterday I posted the final exam. So it's on Canvas, and there are links on Slack and um, Canvas to that. We can go through that today. Also, if there are any questions about any of the assignments, past or coming up, or any questions about the exam, that would be awesome. Otherwise, I can talk a little bit about the correctness of loops, if there are questions about that. But my first thought was to go through the exam, but if there are any questions about anything else before we do that, that would be totally awesome. So any questions about anything else before we kind of run through the exam quick and see what's going on there? Okay, well, let's have a quick spin through the exam. So this should be the exam. And it should be similar in structure to the second exam. I think it's also at least similar in length to the second exam. I would guess. I mean, it's always a little hard for me to judge lengths of things, but I think it's probably in the neighborhood of the same length as the second exam, with more emphasis on the most recent material because that's the stuff we haven't had an exam on yet. So I think all of this is pretty much old news. So there's an old chapter 1 problem on our friend Leibniz from way back when. So there's the 3 possible values for the question mark. Like, I'm pretty sure we did this problem on the board at some point. Um, but make sure that you include the substitution that goes along with each value or each expression that you put here, because that's going to be an important part of it. Questions about that? Okay. One proof from chapter 3, which is to prove theorem 384b. And I've given you a fairly substantial hint. If you start with either side, doesn't matter which, and you use one of the definition of implication rules to rewrite this without the implication, if you do it in the right way, it will match 3.84a very nicely, and then the proof falls from there pretty easily. So questions about that? Knights and knaves problem. So we have Ted, Sally, and Peggy. Ted claims I am a knight or Peggy is a knave. Sally says, if Ted is a knight, then I am a knave. Big hint, that's probably an implication. Peggy tells you Ted and I are different. And so your task is to translate each statement into logic and solve for which folks are knights and knaves. So it's important that you actually do logic to solve for the solutions, not just kind of infer through intuition or some hand wavy English or something. For full points, you need to actually do the logical calculations to figure out what these people are. So questions about that?
So we would, if we were to go with the right side per se, we just write the right hand side down and then go from there. We wouldn't write the whole.
You're talking about this guy here? Problem 1 or problem 2?
Yeah, problem 1.
Oh, yeah. So I was thinking you would pick a side, start with that side, and go down, and then eventually get to the other side. So something like, let's see, to prove, oh, stop it. It moved my control bar down on top of the thing I was sharing. To prove P equivals Q, I can start with P, equivals some stuff, equivals some stuff, equivals Q. So here I'm trying to prove that this left-hand side equivals this right-hand side. So and you could do it by having the whole thing and showing the whole thing is equivalent to a true statement. But I think you end up writing a lot, and it's less writing if you pick a side. And it doesn't matter which, because the two sides are super symmetric. But if you pick a side and then rewrite that side and rewrite until you get to the other side. But it's entirely up to you. If you find it easier to have the whole thing and to rewrite the whole thing, so as an alternative, right, we could say P equivals Q rewrites to something, rewrites to something, rewrites to true, or a theorem, right? That both of these would be totally reasonable. I have no problem with either one of them. My suggestion, recommendation is too strong. My suggestion here would lead to a proof that looks more like this blue one on the left. But, if you prefer this, the green one on the right, I got no problem with that. Did I answer the right question there?
I was going more on the lines of if we were going to start with P and Q, we'd have to solve for both. We couldn't just choose a side and then go from P to Q, or like underline P and then take P separately and go to Q.
What are you calling? Are you calling P and Q the same things I called them here?
Yes.
And so say that again, what you were suggesting, because I got lost there somewhere. I'm sorry.
It's all right. So I was suggesting that we write out the whole statement.
Okay. Oh,
And then,
underline one of them and then go from there.
yes.
No, I do not want you to do that.
All right.
So let me actually, I'm going to stop sharing this. We'll come back to the exam, but I had enough people do this. I want to actually like nip this in the bud. So I want to share whiteboard because I want to be clear that on what I think Kyle's saying and that's not what I'm looking for. So if I'm understanding you, Kyle, and correct me if I'm wrong, let's say we want to prove, okay, let's say the goal, oh, stop it, little computer. Move out of the way. There we go. So the goal, the claim is, I don't know, let's say P or Q equivals Q or P. What I would not want you to do is like underline one side and say that that's equivalent to, by the golden rule, P equivals Q equivals P and Q. Because it's just not true that this equivals that. The bit you underline equivals that, but what you have written here is this whole expression. And this whole expression just is not equivalent to that. So this, I think, is a bad way to write things up, because unless the reader can infer what you mean by the underlining here, you have written something that just is not true, right? So I don't think that's a good way to do it. I think I would, and I realize, this involves a little extra writing, but it's not that much. I would say claim, P or Q equivals Q or P, and then proof, and then start with one side. Right? And then go down from there and then eventually presumably get to Q or P on the other side. But you want what you write here to be true all the way through. So you want to start with the left-hand side and get to the right-hand side. I don't think this is a good plan. And to make it clear, Kyle, and I don't actually remember if you did this on the second exam, but I do know many people did. Whether you were one of them, I don't know. But to make sure it's that I'm not just singling you out, a number of people did something like this on the exam, and I tried to make a note of it, but I may not have done it consistently. So I'm really glad that you asked so that I remembered to say something about it here. So this good, this not so good, okay? And I might well take off points. I didn't on the second exam for this, but on the final, I reserve the right to take off points for this kind of write-up. Not a lot. I mean, if the proof's right, you'll still get most of the points. But this is really technically not correct just because this is not equivalent to that. If you don't sort of understand what the underlining means, the two pieces are just not the same. So did that answer the right question?
Absolutely.
Okay. And I apologize if it sounds like I was calling you out there. Like I said, lots of people did something like that. So I'm not, dissing on any individual. Just as a general strategy, much prefer the thing on the right to the thing on the left. So, questions about this before we go back to the exam? Okay, stop that sharing. Start a new sharing. Go back to the exam. Share. Okay. So, so that result. Were there any other questions about problem 1 or problem 2? Okay. So then we jump to chapter 9. So there's a proof from chapter 9, body weakening, strengthening. So we have that if we know exist X RP, then we know there exists X with range R and P or Q. I would definitely start with the right-hand side because it's got the Q in it. And we want to make the Q go away. And that's easier than making the Q appear. You will need something from chapter 8 to make this work. So be thoughtful about that. Questions about problem 3? And then problem 4 is similar to one of the if statement proofs in the book, and one of which is on the homework. So using proof method 10.5, show that this is correct. And I'd be happy to talk more about if statements in class today, if that would be a thing people would like to talk about. There's at least one piece that I want to mention that's not crucial, but might be helpful. So questions about problem 4? Then there are 2 induction problems, a simple summation one. So this is similar to the kinds of things that are in 12.4, but with way simpler algebra. So there's no sort of nasty algebra trap in this guy, because everybody loves nasty algebra traps. And then the other one, here, I'll keep them both on the screen, is a factorial problem. So we're proving that the sum of I times I factorial is n plus 1 factorial minus 1, which is not at all obvious. It's not clear to me that, 0 times 0 factorial plus 1 times 1 factorial plus 2 times 2 factorial up to 10 times 10 factorial is equal to 11 factorial minus 1. I mean, why would that be true? Yet it turns out it is, and you're going to prove that it is on the exam, which is, I think, kind of nifty. Now, one thing that people were clearly confused about on some of the homeworks, at least based on questions, there were people who I think thought factorials needed 2 base cases because factorials had been in kind of the same part of the book as Fibonacci's, and Fibonacci's had needed 2. Factorials typically only need 1 base case. And the way we know that, or the way to see that that's probably true, is if we think about the definition of factorial. So n factorial is n times n minus 1 factorial. This only refers to one immediately preceding instance, right? 5 factorial is 5 times 4 factorial. So it only looks back, if we think in terms of our stepping stones. So 0, 1, 2, 3, 4, 5. the recursive definition here only looks back one step, which is different than Fibonacci, which looked back at two of the preceding steps. So the fact that factorial only looks at the immediately preceding step, it only refers to the immediately preceding case, means we only need to do a base case that's just for 0. We don't have to do 0 and 1 as separate base cases. It's not wrong to do more base cases. You're proving more than you needed to, which isn't incorrect, it's just wasteful. So we only need to worry about this 0 case. We don't have to worry about 0 and 1 because we can do 1 using 0. 1 is able to, we can deal with 1 just using the definition, whereas we can't deal with fib of 1 using the definition of fib because it would require 0 and -1, and we don't have a fib of -1. So that's why we have to do 1 as a separate base case, because we can't use the recursive definition to figure 1 out. And we can start with 2 with Fibonacci's because we've got the 2 previous ones to use, but we don't have it for 1. But with factorial, we just need the immediately preceding one. So we can do 0 as a base case, and everything else we can deal with by just looking back at the previous instance. Okay. So you only need, that was a long way of saying you only need one base case here. Questions about either problems 5 or 6? Okay. So problems 7, 8, and 9 are related to material we really haven't covered in 12.6, none of which need to understand what's in 12.6 to solve them. We'll scroll down in a second. They're simple problems that you don't need any of the chapter 12 stuff to do, but they're motivated, they exist, and they're interesting because of things in 12.6. So if and when there stop being any questions, I will actually sort of back up to these last 3, section I, and try to actually talk through why we would care about these 3 proofs. I need to clear my annotations or I'm going to have scribbles all over everywhere. And that's going to be bad. Okay, so let's ignore this for the moment and we'll just talk about the problems. And then I'll try to explain where they come from and why we care about them in a bit. So first, just to simplify, I'm using these 3 definitions, Q, P, and R. And this is all actually based on exercise 12.42b from the textbook. So you can go look at that and it'll have all of this stuff in it. So I didn't just dream this up. This is all from a real problem. So Q is n is at least 0. P is k is between 0 and n, inclusive on both ends. And x is the sum from 0 up to, but not including k, of b of I. So b is an array of values, and we're adding up the first k values in that list of values. And that sum of those first k values is going to be x. That's what P tells us. And R says x is the sum of the first n, which is essentially the whole list. So R is saying x is the sum of the whole list of numbers. This part of P here is saying x is the sum of the first k values in the list. Okay. Questions about Q, P, and R? So then we have 3 problems, 2 of which are correctness proof problems, and 1 of which is just a chapter 3 problem, essentially. So the first problem, problem 7, says if the with a precondition Q and this little program, this assignment statement, show that we get to P, okay? And so that would be using proof method 10.2 on assignment statements, and you just plug everything in and solve. And it's very straightforward. Now, one thing you can do that might help clean up the writing a little bit is P is kind of large, right? Your post condition here is sort of big. And if you remember proof method 10.2, this is going to be Q implies P with this substitution implied. So the right-hand side of your implication is going to be this big thing with a substitution applied, which is still going to be a big thing. And so if you want, because this is a conjunct, we have this and this, it's acceptable to do that as two steps. One, to show that Q gets us to the first conjunct, and the other that Q gets us to the second conjunct. So we could do that in two pieces if you want. And in fact, because this is also a conjunct here, namely it's 0 at most k and k at most n, you could even break this down into three pieces. You could say Q followed by this gets you to 0 at most k, Q followed by this gets you to k at most n, and Q followed by this gets you to that. All of those would be possible. So you could do it, you could keep P together and just do the whole thing as a big P. But if you want to break it down into smaller pieces to help keep things straight in your head, I'm completely fine with that. That is not a problem. So up to you. There it is. That was a lot of words. Questions about that? Okay. Then problem 8 is a similar thing. We assume P and K not equal to N, and then we want to get back to P after doing this assignment. So X gets X plus BK, and K gets K plus 1. And again, so this is again just 10.2, and all the comments from the previous problem about breaking P into pieces apply here as well. So if you prefer to break P up into chunks, that's fine. One thing to check is just a sanity check when you think you're done, is make sure that somewhere you use the fact that K is not equal to N in some part of this. It's not necessary everywhere, but it does need to be used somewhere. If you're never using this anywhere in your proof, it's a sign you may have missed a situation that you need to be thoughtful about. So that's something to check for. Okay. Questions?
How will you do that exactly? Like,
well, I mean, looking at your proof, somewhere you probably needed, let me, annotations again. Somewhere, there probably should have been blah, 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 equivals by something, something, noting that K not equal to N, blah, blah, blah. Or maybe it's just assumption that K not equal to N, right? You need somewhere to have done something that only works if K is not equal to N. There should be some step somewhere that needed that fact, okay? And there are a couple of ways that could play out. In some of the earlier problems, and this is not, I'll actually change this to be red here. This is not the right thing here, but if you'd had at some point, oh, I don't know, E equals K minus N times something, 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 and you wanted to turn this into E over K minus N equals something, 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 you can only divide by K minus N if this is not 0. So you might need to say noting K different from N to make it clear that you're allowed to divide by K minus N and it won't blow the world up. Now that's not what you need to do here, but that there in some of the algebra and some of the chapter 12 problems, that was a place where you needed to check, or you would need to note that, you know, it's okay to divide by this because we know that's not 0 because of some assumption. In this instance, it's actually more about note that we're adding 1 to K. So K is replaced by K plus 1. And that in P, one of the assumptions is that K is less than or equal to N. So we need to know that adding 1 to K doesn't break this, that making this bigger doesn't push us past N. And that this turns out to be important for that. So in this case, it's about not breaking this part of P that matters. Did that help some?
Yeah.
Okay. Other questions about 8? And then I'm going to clear all these drawings because they'll be in the way. And then 9 is really just a chapter 3 problem. So that P and K equals N implies R. So yeah, that doesn't even use this chapter 10 stuff. This is just a straight up chapter 3 thing where P is this big piece here. And you say that, and K equals N gives us R, which is this guy here. So and that's the last question on the exam. So questions about the exam, about any of the homeworks, about anything we've done all semester, about what's happening between now and the end of the semester, anything.
I guess I have a question on number 5.
Okay. Here?
Yeah, so when we do the induction step, are both sides of that equation going to have to get the n plus 1? Or is it like just the left-hand side?
Oh, they will both have to get the n plus 1.
Okay, yeah.
So because if this is P, let me turn on annotation again. If you think of this as P of N, then P of 0 is replace all of the n's with zeros. So sum I, 0 at most I less than 0, P times I squared equals P times sum I, 0 at most I less than 0, I squared. And P of N plus 1, we will have to replace all of the n's with n plus 1. So we'd have the sum over I, 0 at most I less than n plus 1, P I squared equals P sum over I, 0 at most, I less than n plus 1, I squared. So it's crucial that we replace both of the n's with n plus 1, and then replace both of the n's with 0. If we don't replace both of them, this stops being true, right? Like this would be, if we had p times 0 squared plus p times 1 squared plus p times 2 squared plus p times 3 squared. And so let's assume this is 4. So we go up to 3, but not to 4. If we just had n over here, we'd be missing that last term. So we'd have 0 squared plus 1 squared plus 2 squared plus, we'd be done. So if we didn't increment n on both sides, we would get something that just isn't true. So you got to make sure you have n plus 1 on both sides, or this equality just doesn't hold. Did that answer the right question?
Yes, that did. Thank you.
No problem. Other questions?
Since it's been a while, could we do an example of problem 0?
Sure.
Or like more to that?
Yeah, totally. So, helps a lot if I erase my annotations, doesn't it? Problem 0 is one of these Leibniz problems. Let's see. May have to make up one because I'm not sure. Yeah, let's make up one that'll be similar. So I'm going to switch over to the whiteboard. Does anybody have any questions or anything about this before we switch over to the whiteboard and do a similar but not the same problem? Okay. So I'm going to stop sharing this, and then I'm going to share the whiteboard. Oh, look, the whiteboard's still there. How exciting. And I'm going to make a new page so we don't clutter up the world. I'm going to have as an example, let's see. Let's say we know A is B squared plus 1. And we want to then infer that A times A equals something. Okay. So now Leibniz says that if we know two things are equal, we can replace instances of one side with instances of the other side. So in this case, we could replace an instance of B squared plus 1 with A if we wanted to. And we can replace A's with B squared plus 1. So we can go either direction. This one will specifically go from a to b squared plus 1, but we could go the other way. Now, when we have two instances, two or more instances of one of the sides, then we have a problem of we could replace this a, or we could replace this a, or we could replace both of them. And so that gives us three options. And all of them are legal, right? There's actually, in some sense, a fourth, which is to replace no instance of a, but then why are we here? There's no point in doing this if we're not going to replace something, probably. But if we're going to replace something, we've got three choices. Replace the one on the left, replace the one on the right, or replace them both. Okay? And all of those are legal. Does that part make sense? That's actually pretty critical to the whole exercise.
I would say so.
Okay? So then there's the question of how do we specify which ones we're replacing? And that's the expression part. So we have, if we have, for example, E, so we got three options. Three options. I'll call the first one A. If E is Z times A, then if you remember the rules about Leibniz, what this tells us is that we have this. So this is like capital X, and this is capital Y. Oh, I did that badly. Well, whatever. That tells us that E with Z replaced by capital X, oops, that should have been an 8. Oh no, that was fine. I am losing my mind. E Z replaced by X equals E with Z replaced by Y. And so here in this example, if E is Z times A, this turns into A equals B squared plus 1. E here is Z times A, so this is A, and this is B squared plus 1. So this is going to be A times A equals, and here we're saying Z gets B squared plus 1 because A is equal to B squared plus 1. And the fact that there's a Z here but not there means we're only replacing the first one. So in this first case, we know that these two things are equal. So we know this equals this, where we've replaced the first A with B squared plus 1. And we've used this expression E to justify that step. And it's the having the Z here but not here that tells us to replace the left hand but leave the right hand alone. Questions about option A before we do B and C? And then B, if we want to just replace the one on the right, we say E is A times Z, and then we have A equals B squared plus 1 is E with Z replaced by this is A times A. E with Z replaced by this is A times B squared plus 1. So this tells us that we're replacing this guy because that's where the Z is. And then C, third option, if we put Z in both places, then we get A equals B squared plus 1. And we infer, well, we replace both Z's with A. So we get A times A. And on the right-hand side, we replace both Z's with B squared plus 1. And we get that. So those would be the three solutions. And so you'd have, at a minimum, you would need to provide the expression E and the instance of Leibniz, or at least the question mark E bit, which would be that part there, for each of the three of them. Questions? Does that make sense? Help?
This helps.
And it had been a long time, so that was, I think, an excellent question. And I suspect that seeing that again looked very different from the perspective of early May than it did in late January. So this is a kind of class we're going back and redoing it all. I think your second experience would be very different than your first experience. Questions about this? Other questions about the exam or anything else before I do some, well, actually I want to talk strategy a little bit, and then I want to talk about proving loops if there's nothing else going on.
Actually, could we do a Leibniz as an axiom problem?
Sure.
Also for the same reason.
Yep. So let's see. Leibniz is an axiom problem, end of chapter 3. So let's let me make a new page here. So let's start with just the axiom. So axiom 3.83, Leibniz as an axiom. Says that E equals F implies E with Z replaced by big E with Z replaced by little e equals big E with Z replaced by F. So this is telling us if we know two things are equal, then we know any expression with some variable replaced by the left-hand side of the equality is equal to the same expression with that variable replaced by the right-hand side of the equality. So in our little example before, if we were like A, let's say E is A times Z, then A equals B squared plus 1 implies A times A equals A times B squared plus 1. So that would be an instance of 383, okay, with this particular E. Does that make sense? Questions about that? And now to prove something, I'm trying to think of what would be a good one to do. So let's do 384C. And hope I managed to get there. So the claim is Q and E equals F implies E with Z replaced by E, little e, equivals Q and E equals F implies E with Z replaced by F. So that's what we're trying to prove. Now, proof. The book suggests using shunting, which makes me think we're going to want to start with one side and get to the other, because shunting has the form P and Q implies R. So shunting kind of matches either of the sides. It doesn't matter. The sides are quite symmetric. But it seems to me that we probably want to pick one side and try to write until we match the other if we're going to start off with shunting. So I'm going to pick the left-hand side because I don't see any reason to, care. So Q and E equals F implies E with Z replaced by E. We're going to use shunting. Which is, I guess I should give that a number. Shunting is 365. Now, there is a question about which of these two pieces we want to pull out, because we could make it Q implies stuff, or we could make it E equals F implies stuff. And in fact, both should work, but in different ways. So I'm actually going to try it both ways, I think, and see sort of what that looks like. So the first one, which is in some sense the more obvious, is I'm going to just pull the Q out because that's the one that's leftmost. And that shunting tells us that Q implies this implication. Now, at this point, so questions about the shunting step? This now matches exactly the left-hand side of 384B. So this allows us to then use 384B which is the thing you're trying to prove on the exam, and rewrite that as Q implies E equals F implies E with Z replaced by F. And that looks promising because we now have this matches that guy, right? So we've converted from the E1 to the F1, and that seems like a win. And in fact, if we just use shunting backwards, as it were, here, we're done. Q and E equals F implies E with Z replaced by F. That matches our right-hand side. We're finished. Yay! Okay. Questions about that before I do another proof, another version of this proof? Okay. So let's do proof 2. So we'll start with Q and E equals F implies E with Z replaced by E. And now I'm going to actually pull out the E equals F in my shunting step instead of pulling out Q. Since and is symmetric, I could swap the order of these and then, but I'm just going to do this in one step because we've gotten so good at this by now that we don't really need to do all those little things. Okay, so we have this implies that implies that. So, okay. Questions about that step? That step's important. If there are questions, it'd be good to ask. No, I'm trying to think what would be the right thing, the right way to do this. So now we would use B again, but in a different way. So B says that if you have equals implies something with little e in it, then that is the same as equals implies this with the little e replaced by little f. So we would get E equals F implies Q implies E with Z replaced by F. So that's a more complicated use of 3.84b, but it still gets us to the same place. And then we use shunting again, sort of backwards. And we get Q and E equals F implies E with Z replaced by F. And we're done again. I think I like the first one better, to be honest with you, but they both would work. Questions about that? Did that help out?
Yeah, that definitely helped.
Cool. And as a pro tip, the assigned problem is 384b, which means you don't have a lot of other options in the Leibniz's axiom section to work with. So, you're going to probably need one of the other Leibniz's axiom things, and you don't have many to look at. So I've deliberately chosen something where there aren't a lot of options. So it's hard to get too lost in this one. If you just sort of look at what your choices are, hopefully it will play out. Other questions? So let me talk strategy for a little bit, and that'll actually probably wrap up class, and we'll finish the loop stuff on Friday, unless there are more questions, right? We don't have to ever do the 12.6 loop stuff because you don't need it for the exam. It just would help explain why some of those problems are what they are. But I want to talk strategy for a second because I think that one of the things that I saw in the second exam were some strategic issues, like the way people approached doing the exam either helped them succeed or led to problems. And so because we're not all in the same place, it does make it harder for you to access me. You can't just sort of wander around the science building looking for me. You can't come by my office and hope that I'm there. And that makes things more difficult. And I apologize for that. I wish there was some way that could be different, but obviously it's not. I've been back to my office once since spring break. And I had something that belonged to somebody else that I had to go get. And the building was weirdly empty. It was very kind of creepy. So, you're not going to find me there. So how do you deal with this? I think that, as always, start as early as you can reasonably start. And I know you've got other projects and final papers and, a million things going on. So I realize that this is not the only thing you're doing. But I would start as early as you can. I would spend as little time on a problem as possible. If you get stuck and you've spent 5 or 10, 15 minutes being stuck, depending on sort of what your pain threshold is, you should stop. Like, there is no point. If you spend half an hour, 45 minutes on any of these problems and you're not getting somewhere, you are definitely not using your time well. Do not do that. If you spent some time on a problem and you're stuck, you should stop. You should make a decision about, do you want to stop and come back to it later on your own? Maybe some distance and some sleep or food or taking a walk or whatever it is you do to clear your head will allow you to see it fresh when you return. I don't know, right? That's a choice. But you can also take a picture of what you've got and send it to me. Send it on Slack, send it in an email, whatever, and say, hey, this is where I got to, and I don't know what to do next. Or I don't know if I used rule blah, blah, blah correctly. Or I've looked at problem X for 20 minutes and I have no idea how to start. Can you give me a hint? And it's my job to decide what I can and can't tell you. Don't be shy about asking questions. Just ask questions, and I will try to help you. Maybe I'll respond with a question. Maybe I'll respond with a hint. Maybe I'll point out that you made a mistake on the second step, and that's messed up everything after that, and that's why you can't get anywhere from where you are. But definitely ask. I am happy to take questions like that. And that only really works if you start early enough that you have time to send me something. You have time to wait for me to see it and respond to it. And then you have time to act on the response. So, not good to be doing that half an hour before the exam is due. So start early. Don't spend too long on any given problem. Check in with me early and often. I have set aside appointment slots Monday, Tuesday, and Wednesday of next week from 9 a.m. to 4 p.m. or something like that. I mean, great big chunks of the day. So, if you want to talk face-to-face, grab an appointment slot. There are several left in what's left of this week. There's some today available today. And then there's piles of them at the beginning of the week. So if you have looked at the exam over the weekend and you've got like 3 or 4 questions and you'd rather talk on Zoom than, send me stuff on Slack or by email, by all means, grab an appointment slot and we can have a conversation. And that would be awesome. So, use those resources. Don't wait until the last minute, and don't be shy. I think there are people who feel like somehow if they can't do it themselves, then they just, shouldn't do it or something. Don't be shy about asking questions. And if you want me to look something over because you're not sure if you're doing it correctly. So there was the question about that very first problem with the Leibniz and the expressions. If you're like, I don't know if that kind of problem always confused me, and I don't know if I'm doing it right, I'm happy to look at what you have and tell you, yeah, that's great, or no, we should like have a Zoom meeting and talk about that, or this is close, but if you do this, that would be more correct or more complete or something like that. So don't be shy about asking questions. So I think that's my strategic tips is, start early, don't spend too long on any problem, ask a lot of questions, okay? And if there's anything I can do to help, I realize this is like way crazy difficult time. If there's anything I can do that would assist you in some way, let me know. I'm here to try to like help out, okay? Okay, that is 10:20. Are there any questions in the 0 minutes remaining? I will see everybody on Friday, and we will take more questions, and or we can talk a little bit about proving the correctness of loops if there's time, okay? So hang in there. Semester's almost over. You will make it work. And I will talk to everybody on Friday, if not sooner. Ciao.
Hold up, Nick.
Yep.
For like the Leisman problem, the problem 0, are you allowed to replace the 7, or is that just?
Oh, no,
Okay.
you. Oh, yeah. No, you are replacing the 7. I'm sorry.
Okay.
Yeah, the 7 is the thing you're replacing in that example.
Okay.
Does that make sense?
Yeah.
Cool. Anything else?
Nope.
Cool. Talk to you later.
Bye.
Bye.